is Trey Arwood. I am the narrative expert for the team.
My name is Shirin Rajamani. I am the coding expert for the team.
My name is Cole Gutierrez. I'm the quality control and analog expert.
So the objectives for this endeavor were really to design techniques to control the motor of the EV vehicles and reach them to desired speeds or destinations. That was kind of the desire, and so we had to implement and find ways of doing that. The way we modeled that at our consultancy was to model the EV drivetrain with a wheel that was connected to an electronic gear motor via a gearbox, and this provided accurate enough results to help predict the real world implementation of a vehicle. And the specifications generally were 0 steady state error, a percent overshoot and undershoot around less than 2%. We wanted a rise time larger than 0.1 seconds, a small initial slope, 2% settling time less than 0.2 seconds, and a voltage that's less than 24 volts for our model. And our design process, generally over this last semester, we started with setting up electronics. We had an Arduino microcontroller, and so starting with our general coding, and then we went into the mathematical models to first have theoretical basis for the work that we're doing experimentally, and we did that with electronical and mechanical components. Then we tested the different speeds of the controllers to try to find the ideal one for our client, and then after that we finalized the controller, and now we're pitching it.
So this is the timeline of our lab. Starting in lab 1, we found the dry and the viscous coefficients for friction. Going on to lab 2, we found the relationship between the DAC and the voltage that was actually given to the motor, because the Arduino can't provide direct analog to digital. We have to use a DAC to convert that. We also found the motor resistance and the motor back EMF constant. In lab 3, we plotted some Bodie plots to look at the different magnitude and phase. And we then could use that to back calculate the KP, the constant proportionality. Then in lab 4, we tested which would be better, a PI or PD controller. We determined that a PI controller was going to be our most optimal based off of our graphs and some later slides. And then we spent lab 5 designing the mathematical models we would need for that particular controller.
So as you can see on the left, we have just a PD controller. The desired speed we set was 12 radians per second, but it wasn't really able to reach that. It only reached around 4 radians per second. So we decided not to go forward with that. Then we decided a PD controller with a low pass filter. It was a little bit closer to the theoretical, which was still only 4 radians per second, not the desired 12 radians per second. So again, we had to scrap that idea. Finally, our final idea was a PI controller, which was able to reach the 12 radians per second, which was also the theoretical and the actual. So, as you can see, the differences between each controller, there was clear differences. PD controller was not able to meet the 12 radians per second. Even with the low pass filter, it still wasn't able to meet the 12 radians per second. However, the PI controller was able to meet it and stay constant at that value. So, we also had to alter it a bit to meet the client's needs. For the client's needs, we utilized the PI controller, like I mentioned, and added a low-pass filter to reduce the noise when reaching a steady state. The trade-offs we had to make were that the PI controllers have a little bit more oscillatory stability compared to PD controllers, which are a little bit more stable when they reach steady state, which we can also mitigate with just a low-pass filter. As you can see, the image I included was the transfer function. So from the controller that we just designed from the transfer function, as you can see, we were lower than the 24 volts as shown by the graph on the left. We were able to meet the rise time and settle time specifications from the graph in the middle, and we were able to design it by using the root locus and the white zones on it from the graph on the right. When we actually tested it together, as you can see, our actual steady state was met. So we were able to easily meet the 12 radians per second, and it was similar to the theoretical output that we found.
And so our assumptions generally that we took during this lab was the relationship between angular velocity and voltage, and we also assumed that there was dry and viscous friction through damping coefficients. And so some simplifications, like mentioned at the start, but are important to take into account once these results are given, is that we model this with the wheel connected to an electronic motor, and also that the equation of motion of a straight road was generally analogous to the equation of motion of the spinning wheel, and therefore it's not going too far to use that. And different implementations for the future include grid integration, as the direction of energy and electricity flows bidirectionally. For charging rates, we can control and reduce harmonic distortion through a controller. And then also just for the HVAC systems within the vehicles, we can use a control to control fan speeds, noise, other things that are going to be important as cars even get quieter and more efficient. So thank you.